So what we're going to be talking about today is power in three-phase circuits. So the first thing that I want to talk about is instantaneous power. And this isn't something that we talked about when we were doing power in single-phase circuits. So I'm going to introduce that real quickly, just to kind of show you how instantaneous power in a three-phase circuit is vastly different. Okay. So I'm going to call this instantaneous power single phase. So if we have a network that is sinusoidally excited, it really doesn't matter what's inside this black box as long as it's linear circuit elements. So resistors, things we can model as resistors, capacitors, inductors, etc. Just, I don't care about that. And we excite this network sinusoidally, measure the voltage drop across the network, V of t, and the current flowing into the network, I of t. In a single phase system, we know that V of t will be of the form Vm cosine omega t plus theta v. And I of t will be of the form Im cosine omega t plus some phase angle theta I, right? This is pure review of the sinusoidal steady state circuit analysis that we did at the beginning of this class. So I have these two sinusoidal signals. My instantaneous power, P of t, I'm not going to derive this, it's just a trig identity, is going to wind up being simply the product of our voltage V of t and our current I of t. And this is going to come out to 1/2 Vm Im cosine, theta v minus theta I, plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I, where we have some DC component right here. And this is literally nothing more than the average power. And then we have an AC component of the power over here, which doesn't really have a name. One thing that's interesting to me is that this AC component is actually oscillating at twice the angular frequency of the voltage or the current. So if I were to plot this instantaneous power, and bear with my inability to draw a sinusoid to save my life. It might look something like this for an inductive load. So where this part right here represents my average power, okay? So that's what instantaneous power would look like for a single phase circuit. We can see that at any given point in time, the power that's delivered to our load is constantly changing. It's a sinusoidal signal that is effectively superimposed on top of this DC steady state signal that we commonly call the average power. Now, in a three-phase system, we would have something extremely similar, except that we would have three different phases of our voltage waveform and our current waveform. So if I were to represent this with a simple picture, just for the sake of argument here, let's say that we have a YY system. The voltage drop across each phase of our load as a function of time, so this would be VAN of T. And our current flowing in, so I'll just represent it right here, would be IAN of T. And our B and C phase would also have some associated time varying voltage and current flowing through it, right? If there's time varying voltage and current flowing through the A phase, then there has to be a time varying voltage across and time varying current flowing through the B and C phases as well. Not drawing them on here just because it would make the diagram too busy. So our instantaneous power absorbed by our load as a whole would be the power absorbed by the A phase. Let me put that as a capital A since it's on the load side. The instantaneous power absorbed by the B phase and the instantaneous power absorbed by the C phase. Traylon.
With instantaneous power, is it instantaneous because we can plug in the time that we were looking for?
Exactly right. So this is how we would be able to map the given amount of power at any particular individual point in time. You're 100% correct.
I derive power, like what is
No, it's the same thing. It is literally the same thing. So power as a function of time is the instantaneous power. 100% correct. So our total power absorbed by our three-phase load would just be, or total instantaneous power absorbed by our three-phase load would just be the instantaneous power absorbed by the A phase plus the instantaneous power absorbed by the B phase plus the instantaneous power absorbed by the C phase. Nothing, I don't think, too wildly difficult about that. So we could say, based on what I have up here for my single phase equivalent circuit, or excuse me, single phase instantaneous power, PA is going to look something like 1/2 VM IM cosine theta VA minus theta IA plus 1/2 VM IM cosine twice omega t plus theta VA plus theta IA. The instantaneous power absorbed by load B, or the B phase, is going to be 1/2 VM IM cosine theta VB minus theta IB plus 1/2 VM IM cosine twice omega t plus theta VB plus theta IB. And I want to look at this one a little bit really quickly, okay? So we know that theta VB and theta VA are related to each other. They're the same angle except that theta VB is just 120 degrees in phase behind it. Theta IB is the same angle as theta IA except that it's 120 degrees in phase behind it. So this subtraction here let me express it like this. So this guy right here is theta VA minus 120 degrees. This guy right here is theta IA minus 120 degrees. So when I subtract theta IB from theta VB, what am I going to get? I'm going to get theta VA minus theta IA again. The 120 degrees phase separations on both the voltage and the current are going to wind up canceling each other out. So I could express my instantaneous power for the B phase as 1/2 VM IM cosine theta, VA minus theta IA plus 1/2 VM IM cosine twice omega t. I'm going to do the same thing over here, so I'm going to have theta VA plus theta IA minus 240 degrees, because now those negative 120s add together for this part. Okay. So effectively, the instantaneous power for the B phase looks exactly like the instantaneous power for the A phase, except that it's lagging by 240 degrees. If we went ahead and looked at what's going on in the C phase, we would formally have PC of t would be 1/2 VM IM cosine theta VC minus theta IC plus 1/2 VM IM cosine twice omega t plus theta VC plus theta IC. And looking at these angles, we know that theta VC is just theta VA minus 240, and theta IC is just theta IA minus 240 degrees. And so we're going to see a similar canceling out on the DC term and a similar adding of the lagging on the AC term. And so that's going to look like one-half VM IM cosine theta VA minus theta IA plus 1/2 VM IM cosine twice omega t plus theta VA plus theta IA minus 480 degrees. Now, what is an equivalent angle to 480 degrees? So let's subtract 360, so 120, okay? So I can change this 480 degrees right here from negative 480 to negative 120. It changes absolutely nothing because I know that there's 360 degrees in a full cycle, right? So I have, let me underline things right here. On the A phase, I have an AC power term that has a phase angle of, let's call it 0, just for the lack of a better argument here. Down here, I have an AC power term that has a phase angle of negative 120 degrees. And right here, I have an AC power term that has a phase angle of negative 240 degrees. And I know that my total instantaneous power is just me adding these guys together. What happens when I add something that has the same magnitude and is 0 degrees, and then negative 120 degrees, and then negative 240 degrees out of phase? So add one angle 0 plus one angle negative 120 plus one angle negative 240 in your calculator for the fourth time in this class. It's 0. All three of those AC powers wind up canceling each other out. And so the only thing that's left is just the DC term, which are all identical to each other. So our instantaneous power absorbed by our three-phase load is just 3/2 times the magnitude of the voltage times the magnitude of the current times the cosine of theta VA minus theta IA. This is really, really interesting because our instantaneous power, which is our time-dependent power, actually doesn't depend on time at all. It is a constant. This is one of the biggest reasons that three-phase power is used in industrial settings, because if you connect a motor to a three-phase source, it receives a constant amount of power, which means it produces a constant amount of torque.
If all of our waves are that like proof for this, like if we have there's three that are fighting, so.
There's three that are fighting, but they all have some DC offset. So the AC parts cancel each other out, and the DC offsets add together. 100% right. Yes. So it was originally negative 480 degrees. If we add 360 to negative 480, what do we get? Positive 120, or excuse me, negative 120. This negative 240 right here would be effectively positive 120 if we chose to think about it like that, but I'm used to dealing with negative angles for everything. You wire it exactly normally. It's receiving DC power only because the AC portions of the instantaneous power cancel out. So we're not hooking this up to a DC source. We're hooking our motor or whatever up to a three-phase AC source. And because of the phase separation that is exactly 120 degrees between the phases, we wind up delivering only DC power to our load. All of the AC bits cancel each other out. So this is instantaneous power, and it's also given us a clue about what's going to happen when we look at our average power, because this is very obviously P average for a three-phase system as well. It is just the DC component of our instantaneous power. Okay. So now let's look at things from a different perspective, okay? So now we're going to look at complex power. I'm sorry, what? Yeah. We're going to see it again in a minute, so you can box it now or you can box it later. We're going to express things in slightly different terms. So I would argue actually, this was just me showing you guys something interesting, and then we'll put it in context of what we're used to dealing with here when we're talking about complex power. Okay. All right, so let's say that I'm looking at a Y-connected load as part of a larger system. Okay, so I don't care how my source is connected or anything like that. So I'm just putting these ellipses here to say like, hey, there's something connected on the left-hand side and we don't really care what it is. So here's our A phase. Here's our B phase. Here's our C phase. And we're going to start by looking at our phase voltages and our phase currents. So this is our phase voltage VAN, our phase voltage VBN, and our phase voltage VCN. And this will be our phase current IAN, our phase current IBN, and our phase current ICN. So I would argue the total complex power absorbed by our three-phase load here is just going to be the complex power absorbed by the A phase plus the complex power absorbed by the B phase plus the complex power absorbed by the C phase. Effectively the exact same thing we did for the instantaneous power. Now we're just looking at things in terms of complex power, right? So we could call this SA plus SB plus SC. Okay. Well, what should SA be? What's our definition for complex power? Fundamental mathematical definition.
E effective, effective.
Conjugate. That's it. So so the V effective is an RMS phasor, right? So here, that would be our voltage VAN. So we would have VAN times IAN conjugate, right? So expanding this out just a little bit more, this is going to look like the magnitude of VAN times the magnitude of IAN with an angle of theta VAN minus theta IAN. So this is just complex power in polar form, right? So here's my magnitude. That would be my apparent power. We'll get to that in a minute. This would be my power factor angle. Magnitude is just a real number. So the conjugate of a real number would be the real number itself anyway. So yeah. So now let's look at the complex power absorbed by the B phase. So using the exact same thing, we would have VBN times IBN conjugate. Well, we know that the magnitude of VBN is literally identical to the magnitude of VAN in a balanced three-phase system, right? All of our magnitudes are the same, only our phase angles change. So I can put the magnitude of VAN here, the magnitude of IAN here. We know that the voltage in the B phase lags the voltage in the A phase by exactly 120 degrees. So this is going to look like theta VAN minus 120 minus theta IAN plus 120. And these 120s cancel each other out. So that the complex power absorbed by the B phase is literally identical to the complex power absorbed by the A phase. It should, sorry, what was that? So I did a little something here. I'm going to write it out for you, and then I'm going to wind up erasing it because it's redundant. So we have theta VAN minus 120 degrees minus theta IAN minus 120 degrees. This minus sign here and this minus sign here cancel each other out to make this guy positive. So what do you guys think is going to happen for the C phase? The exact same thing. So this is going to look like VCN times ICN conjugate, which could be expressed literally as the magnitude of VAN times the magnitude of, IAN with an angle of theta VAN minus theta IAN, because the 240 degrees phase separation is just going to cancel each other out when we subtract it. So ultimately here, we find that the total complex power absorbed by this three-phase Y connected load is just 3 times VAN IAN, or 3 times the magnitude of VAN times the magnitude of IAN with an angle of theta VAN minus theta IAN. So we're going to play around with this a little bit. So one thing that we do pretty often is when all of the magnitudes are the same, we just give it its own name. So I'm going to call the magnitude of VAN a phase voltage designated by the symbol VP. Okay, so that's just magnitude of the phase voltage. By the way, this is not the first time I'm using that symbol in this class. This is how we started off describing our phase voltages when we first started talking about things. The magnitude of IAN is just the magnitude of my phase currents. So I'm going to call that IP. Now, we're going to simplify the magnitude of the angle VAN minus the angle IAN. Where have we seen a difference in angle between voltage and current before? Sure, totally fine. So this is another thing I'm going to write out here just to explain things really quickly, to remind you of something, and I'm going to wind up erasing it because we covered it literally weeks ago. I understand you're not just able to pull that stuff up from just straight memory. Let's say that I had an impedance. Impedance, by definition, is the ratio of phasor voltage to phasor current. Doesn't matter if I'm using an RMS phasor or a regular phasor, right? Impedance is always just ratio of voltage to current. So that would be the magnitude of V over the magnitude of I, and this would have an angle, theta V, and this guy would have an angle of theta I. And putting things together, we would have the magnitude of the voltage divided by the magnitude of the current with an angle of theta V minus theta I, where this is simply the magnitude of the impedance and the angle of the impedance. So theta VAN minus theta IAN is literally nothing more than the angle of the impedance ZY. So I'm just going to put theta ZY here. So we have expressed this, erase all this crap right here, in terms of our generic phase voltage. So we don't even need to know what the actual phase voltage is. As long as we know what the magnitude is, we're good to go. As long as we know what the magnitude of the phase current is, we're good to go. And we just need to know what our impedance is so we can determine its angle. What if I wanted to express this in terms of line quantities? So line voltages and line currents. So let's look up here, right? So this would be my line current, IAA. This would be my line current, IBB. And this would be my line current, ICC. I would also have phase voltage here, excuse me, a line voltage here, VAB. We'd have a line voltage here, VBC. We'd have a third line voltage, VCA, but this is getting too busy, so I'm not going to draw that. You guys all should know where that is by now. So what's the relationship between my line currents, IAA, IBB, ICC, and my phase current, IAN, IBN, and ICN? Say that louder, Trilon. They're the same damn thing, 100%. For a Y-connected load, the line currents and the phase current are literally identical. So what I'm going to do, I'm going to replace that IP with an IL. I'm going to wind up leaving that theta ZY the same because that angle is going to be the same in the complex power. And so now we need to figure out how to express our line voltages in terms of our phase voltages. And really, we're only looking for magnitude here. So what's the relationship between the magnitude of this voltage VAB and the magnitude of this voltage VAN? √3. We don't need the angle, we're only looking at the magnitude. So 3 VP could be written as square root of 3 VL. Because VL inherently is square root of 3 VP by itself. So we would have √3 times √3 VP IP is the same thing as √3 VL times IL. So now we have complex power absorbed by a Y-connected load in terms of phase quantities and line quantities. Now let's do something similar for a delta connected load. Baylor, you got a question? No. Oh, sorry. Right here, yes. Thank you for that. Yes, absolutely. My apologies. Anything else? Sorry for missing that. You're 100% correct there. Well, we're looking, so ZW is the impedance of the transmission line. We're looking at the power absorbed by the load, which is the, ZY, or here in a moment, we're going to be looking at Z deltas. Absolutely. But so realistically, yeah, so what I was going to say is realistically, we usually don't care about the voltage drop across the transmission line, or That's not the thing that we're actually looking for. So what I mean by that specifically is if we wanted the voltage drop across the transmission line, we would usually just say, well, what's the voltage drop at the source, and then subtract the voltage drop at the load from that, and that gives us our thing. So we never do a whole heck of a lot of calculations with what's actually going on in the transmission lines. It's just kind of a side effect of things, would be the best way that I can explain it. So I'm not saying we're going to ignore them by any stretch of the imagination, but all of that information is buried in the other stuff that we're already doing. The subscript P means that we're dealing with phase voltages. Okay, so specifically the magnitude of our phase voltage or the magnitude of our phase current. And the subscript L means that we're dealing with the magnitude of our line voltages and the magnitude of our line currents. We'll put all these into practice with examples here in a moment. So let's look at a delta connected load. A, B, C. So we would have some phase voltage here, VAB, some phase voltage here, VBC, and some phase voltage here, VCA. Here is our phase current, IAB. Here's our phase current, IBC. Here's our phase current, ICA. So once again, we could say that our total complex power is just going to be the complex power absorbed by the A phase plus the complex power absorbed by the B phase plus the complex power absorbed by the C phase. Nothing different than we did for our Y-connected source, or excuse me, Y-connected load. Well, here, SA is just VAB times IAB conjugate, or the magnitude of VAB times the magnitude of IAB with an angle of theta VAB minus theta IAB. What do you guys think is going to happen for the B phase? The exact same thing. What about the C phase? The exact same thing, right? So once again, we find that S3 phase is just 3 times our A phase. And we could express that as, so VAB here is a phase voltage. So VP. IAB is a phase current. So IP with an angle of theta Z delta. Now, so it's the exact same expression that we got for our Y phase, or excuse me, for our Y connected system, Tyler.
Do not have, like, just doing the transformation, make power easier at all. We did transformations to go, there's lots of things, but the power that
Doesn't matter. We're gonna wind up getting the exact same relationship. That's literally all I'm trying to show you here is that you would think they might be different, but it turns out that it is not the case at all, right? So here we have everything expressed in terms of our phase voltages and phase currents, and this looks identical to the relationship that we had for our Y-connected load, except that now we're using theta ZY, so it looks like we don't even care whether the load is Y-connected or delta connected. It's going to work out either way. Putting things in terms of line related quantities. So let's look at some things here. So here's our line voltage, VAB, our line voltage, VBC, and so forth, right? So what's the relationship between our line voltages and our phase voltages for this delta connected load? They're the same thing. They're literally the same thing. Okay. So if we put things in terms of line quantities, we're going to have something, we'll sort that out in a minute. VL and VP are literally the exact same thing because the line voltages and the phase voltages in a delta connected load are identical. We know that our angle is going to be theta Z delta. Now we need to figure out what the relationship between our line currents and our phase currents are. We did this in class on Tuesday. So how is the current IAA and the current IAB related? √3, but it was an angle of -30. Because we're only looking at magnitudes, we don't care about that -30 degrees. So what we're going to wind up getting is √3 VL IL angle theta Z. So it does not remotely matter whether our load is Y connected or delta connected, the exact same power relationships apply. So this was our formal derivation of our complex power. Now we're just going to use what we know about complex power in order to figure out what's the average power, what's the reactive power, what's the apparent power, etc. Okay. So just to recap things here. Our complex power relationship is S3 phase is equal to 3 VP IP angle theta Z in terms of phase quantities. And over here on the right-hand side, I'm going to put things in terms of line quantities. So this will be √3 VL IL angle theta Z. This is what we just arrived. This is where, if you want to start boxing equations, you should start there. The average power is just the real part of the complex power, just like it was in a single phase system. So P, three phase, is going to be 3 VP IP cosine theta Z. And expressed in terms of line quantities, that's going to be √3 VP, VL IL cosine theta z. Realistically, you don't actually have to know this formula. We can do exactly what we did when we were dealing with single phase power analysis and just have our calculator give us the result of our complex power in rectangular form, and then just use the real part of that for our average power. Our reactive power is just the imaginary part of our complex power. So that's going to be Q three phase is 3 VP IP sine theta z, or root 3 VL IL sine theta z. Our apparent power is just the magnitude of our complex power. So that's just going to be 3 VP IP, or root 3 VL IL. And lastly, our power factor is just cosine of theta z. Now, we could also choose to express this as P3 phase over our three-phase apparent power. So power factor definition literally does not change at all from single-phase circuits to three-phase circuits. Just the cosine of theta v minus theta I, or theta s if you want to call it that, or the ratio of average power to apparent power. Here are all of our power relationships, and they are effectively the same thing that we had for single phase equivalent circuits, but now we have options if we're looking at phase quantities and line quantities. So let's work some problems. Yes. So here's problem one. We are told that a balanced three-phase source is used to power the following loads. Then we're given information about those loads. We're told that the line voltage at the loads is 208 volts RMS at a frequency of 60 hertz. And we want to calculate the magnitude of our line currents and the power factor at which our source is supplying power. So I'm going to draw a simplified picture here, okay? So on the left-hand side, I have a balanced three-phase source. I do not know, nor do I care, whether this source is Y connected or delta connected. Here is my transmission line terminal for the A phase, transmission line terminal for the B phase, transmission line terminal for the C phase. Now, nowhere is it mentioned that there is a line impedance that we have to worry about. So we're not going to have any transmission line impedance. So I'm just going to short that to the transmission line terminals of my load over here on the right. I'm not told whether my load is connected in Y or delta, so I'm just going to represent it by a black box where I have access to its three transmission line terminals, like so. So this is a balanced three-phase load. Actually, we have two balanced three-phase loads. So let's connect the second one down here. Just for the sake of argument. So let's call this load one. So I'm going to connect the A phase to the A phase like so. The B phase to the B phase. And the C phase like that. Not pretty, doesn't remotely matter. We are told that load one draws 60 kVA at a power factor of 0.8 lagging. And we are told that load two draws 30 kVA at a power factor of 0.75 lagging. We are also told that the line voltages at our loads is 208 volts RMS, so we just have a magnitude. So effectively, we have 208 volts RMS between the A and B phase, B and C phase, whatever. So we just got told that VL is 208. And we're trying to find what IL is. In part A, and the power factor of the source for part B. So I firmly believe that we work problems extremely similar to this in the context of single-phase systems. And our approach to these problems for three-phase systems is going to be basically the same thing. Okay. So what is the complex power absorbed by load one? How did we do this 2 weeks ago? So the inverse cosine of the power factor, the inverse cosine of the power factor is going to give us the angle of our complex power. Okay, so how do we get the apparent power? What does the unit volt amperes mean? What was that, Owen? That is indeed apparent power. You were already given the apparent power, right? If this were given in watts, then we would divide that by the power factor. We already have the apparent power, right? So this is just going to be the apparent power for load one with an angle of the inverse cosine of power factor one. So that would be 60 kVA. Angle inverse cosine of 0.8. Let me throw this in my calculator. I got 60 angle 36.869. So let's call that 870 degrees. Kilovolt amperes And I'm storing that in my calculator as X for later use. Running out of room here. So let's do load 2 up here. So how are we going to find the complex power absorbed by load 2? The exact same way, because we were provided the exact same information, right? So that's going to be 30 kVA with an angle of inverse cosine of 0.75. Which I get to be 30 angle 41.410. How do I find the complex power supplied by my three-phase source? Add those two together. Absolutely right. So that'll be S three-phase for load 1 plus S three-phase for load 2, which I get to be 89.937 with an angle of 38.383 degrees. So I firmly believe, sorry, what was that? Right here is an S for source. This one is S three phase comma 1 for load 1. This is S three phase comma 2 for load 2. So I'm sorry for my terrible penmanship. So I believe that we have enough information to solve for IL and for the power factor of the source. So somebody tell me how to do one of those. It can't be power divided, voltage divided by power. So let's look at our apparent power relationship right here. So we have the apparent power supplied by our source. That's just the magnitude of our answer. We were provided VL. Root 3 is a constant. So I think that from our apparent power and us knowing the voltage, we can find IL rather easily. Right? So put this over here. So IL should just be the magnitude of S three phase comma S divided by root 3 VL. I get 249.641 amps RMS. So I want to be clear here. Because we were only interested in the magnitude, that's why I chose to use my apparent power relationship. Because apparent power only depends on the magnitudes. If I wanted to know the actual value of the current as a phasor, I would have used the full complex power and effectively done this thing, but taken the conjugate and not used the, yeah. All right, so how do I find my power factor? So cosine of which angle? 38.383, absolutely. Zero 0.784. Is it leading or lagging? Why? Because the angle is positive. All right. First problem's done. Can't come and help you. 208 from literally the problem statement. Yep. So before we move along to the next problem, does anybody have any questions about what we did here? It should, like I said, be pretty darn similar to exactly what we were doing for single phase circuits, except now we just need to pay attention to if we're dealing with line quantities or phase quantities. Okay. What was that, Zach? Yep.
Like we all of a sudden, like stumbling.
Well, for what it's worth, and to give you guys the benefit of the doubt, right before we started working these problems, I did give you 9 equations. So it is, it will take time and practice to kind of unpack and figure out which one is appropriate in which situation. So I'm just trying to provide context and encouragement by saying, hey, you guys have done this before, because for the most part, you have. Just, practice it, train your brain, fire those neurons correctly, all that kind of good stuff. All right. So here's problem 2. We have a balanced 3-phase source supplying power to 4 loads. We're given the line voltage at the loads. We're given a line impedance. And we need to find the line voltages at the source. Okay. So drawing this in a picture form right now is going to be just gross because of the number of loads that we have. So what we might do is very similar to what we did in the last problem, find the complex powers of all of those loads and represent it as a single composite load, which again is stuff that we've done in this class before. So without too much thought going into things here, I hope. Somebody tell me what the complex power absorbed by load 1 is supposed to be. So 20 angle inverse cosine of 0.8. So let's throw that in our calculator. So 20 angle 36.870 degrees, and I'm going to store this in my calculator as X. How do I find the complex power absorbed by load 2? Same way. There's a little bit of a hiccup here, but we'll sort that out in a moment. So 10 angle inverse cosine of 0.7. How do I take into account that the power factor of load 2 is leading? I put a negative sign in front of the inverse cosine. So that's going to be 10 angle negative inverse cosine 0.7, which gives me 10 angle negative 45.573. Storing that in my calculator as y. How do I find the complex power absorbed by load 3? So Baylor is paying attention to the units. That's important, right? So we have 10 kilowatts. Kilowatts represents what part of the complex power? No. Parent power is measured in kVA. That's what we've been dealing with. The real part, which is commonly called average power. Absolutely right. So we have an average power of 10 kilowatts at a power factor of 1. So we would do 10 over 1 angle inverse cosine of 1, which is just literally going to be 10 angle 0 degrees. I'm storing this as Z. By the let me parent. Excuse me. Sorry. Average over power factor, correct. Okay, and lastly, for load number 4, what are we doing there? Same thing we just did for load number 3. Okay. So 10 over 0.6 with an angle of inverse cosine 0.6. Do I need a negative sign in front of the inverse cosine? Nope, because the power factor is lagging. So I got 16.667, which is the same thing as 50 over 3, by the way. Angle 53.130 degrees kVA. Storing this in my calculator as T. And so S 3-phase composite is just those 4 added together. So S 3-phase 1, phase comma 1 plus S 3-phase comma 2 plus S 3-phase comma 3 plus S 3-phase comma 4. So X plus Y plus Z plus T. I got 46.6898. So let's call that 670. Angle 22.932 degrees. Let me make sure that 2 looks like a 2. That looks even worse. I'm storing this in my calculator as A, just because I know I'm going to need it in a moment. Okay. So now I'm going to draw a picture. So over here, I have my source. Over here, I have my load. I'm just going to put S, that is not an S. Composite over here. And connecting my source to my load, I have my transmission line, which has an impedance of 0.02 plus J 0.04. So I'm just going to put ZW is equal to 0.02 plus J 0.04 ohms. Okay. We were told that the line voltage at the loads is 600 volts RMS. So we have VL is equal to 600 volts RMS between the A and B phase, the B and C phase, the C and A phase. That's just a magnitude, okay? Our ultimate goal is to determine the magnitude of the line voltages at the source. So I'm going to call that voltage over here VLS to differentiate it from what we already have. And we are also asked to determine the power factor at which the source is supplying power. So in the previous problem, we were able to say that the power absorbed by the source, or excuse me, the power supplied by the source was exactly the same as the power absorbed by the load. We can't say that here. Why? Because we have a line impedance, which is going to absorb some complex power as well. So we need to figure out how to determine the complex power absorbed by our transmission line network. Okay. So we have an impedance. We have the voltage drop across our load, and we have the complex power supplied by our load, or excuse me, absorbed by our load. So I feel pretty strongly that we can figure out what the magnitude of the current flowing through those transmission line impedances is, right? So the current IL here, only dealing with a magnitude, is going to be the exact same current that's flowing into our load. Are we okay with that sentiment? So how are we going to solve for that current IL? How did we do it 5 minutes ago? Apparent power divided by √3 VL. Right? So IL here is just going to be our apparent power S three-phase composite divided by √3 VL. So what is the apparent power for S three-phase composite? Somebody hit me with a number on the screen. 46.670 kVA. So in my calculator, I'm just going to put the magnitude of what I have stored as A divided by √3. What's the magnitude of my line voltages at my load? 600. So I wind up getting 44.927 amps. Okay. Are we okay with that? Yes. So this 46.670 is in kilovolt amperes. We divided kilovolt amperes by volts, which actually means 0.44, et cetera, kiloamps. And then I just moved the decimal 3 places over to give us amps. So we're playing around with the units to get to 44 point blah, blah, blah. But you actually got the exact same number that I got. I just knew that it was in kiloamps from looking at the units. All right. So knowing the magnitude of our line current, how are we going to find the complex power absorbed by our transmission line network? So I believe you're in the ballpark. Okay. The problem with the method that you just described is that we only have the magnitude of our line current, which means we can only get the magnitude of our voltage. Right? So we don't know the phase angles of our line current or anything like that. Now, I believe that when we were dealing with single phase circuits or steady state sinusoidal circuits, I gave you guys relationships that allowed us to calculate complex power only knowing the magnitudes of voltages and the magnitudes of currents. So that here it would be the magnitude of the current squared times the impedance. However, there are 3 transmission lines. So we're just going to multiply that by 3 to take into account all 3 transmission lines. So this is going to be 3 times IL squared times EW. Just pulling back a relationship from our steady state sinusoidal circuit analysis, right? If I want the complex power absorbed by a particular impedance and I only know the magnitude of the current, it's just I squared times Z, or magnitude of I squared times Z. So three times answer times 0.02 plus 0.04 I comes out to be 6.028 angle 63.435 degrees. What should the units of this be? This is actually very, very important. So let's look at what we did. So I have amps RMS squared times ohms. Okay. Where an ohm could be written as a volt RMS divided by an amp RMS. So that guy goes away and that guy. So I have volts RMS times amps RMS. That's a volt ampere, effectively. Okay? So the distinction that I'm making right here is that the complex power absorbed by our transmission line network is given in volt amperes, but our complex power absorbed by our composite load is kilovolt amperes. So there is a difference in magnitude of 1,000 times. We're about to add those two numbers together, and so I don't want us to overcompensate the contribution of the transmission line network. Okay? So our complex power absorbed by our source would be S3 phase composite. So this is how much was absorbed by our load plus S3 phase times our wire. And so I am going to express this as 46.670 angle 22.932 degrees kilovolt amperes plus 6.028 angle 63.435 degrees divided by 1,000 to put this in kilovolt amperes as well. So what I have stored in my calculator as A plus what I just stored in my calculator as B divided by 1,000 gives me 46.694 angle 22.936 degrees kilovolt amperes. Let's scroll up here. Our goal was to calculate the magnitude of the line voltages at the source and the power factor at which the source is supplying power. So how might we calculate either of those two quantities? Okay, we're looking for power factor and magnitude of a voltage. Caleb. Absolutely correct. So what Caleb has suggested is that the voltage drop, the line voltage at the source is just going to be the apparent power supplied by the source divided by √3 IL. 100% correct. So all right, so complex magnitude of what I have stored as C divided by √3 times what I have stored as D. I've used all 8 variables on my calculator for this problem. So I got 600.059 here, volts RMS. Just to be clear, I am aware that that does not match the 602.650 here. I'd be willing to bet that I made a mistake when I first solved this thing and didn't account for that being in volt amperes and not kilovolt amperes. So our process that we have done for sure is correct. I think I probably made a mistake on that. How are we going to get our power factor? Cosine of 22.936, which I got to be 0.921. Is that leading or lagging? Lagging because the angle is positive. All right, so there is a third problem here. We've only got 20 minutes left, so I would like for you guys to try to start it of your own volition, and then we might finish it together on at the beginning of class on Tuesday. Just so we can all make sure we're on the same page. Your eyes got real big there, you. Yeah. Absolutely. So for what it's worth, what we are going to cover on next Tuesday is 3-phase power factor correction, which is incredibly similar to what we did for single-phase power factor correction, except we have the option of connecting things in a delta-connected capacitor bank or a Y-connected capacitor bank, okay? So realistically, the lecture part of Tuesday's class, we could knock out in 25 to 30 minutes because it's roughly the exact same thing we've already done with one small change. We can use the remainder of that class period kind of as a review session, if you guys want to. So you can ask as many questions as you want about homeworks, concepts, and all of that kind of stuff for the rest of Tuesday, and we got no issue with that. So the should be the Tuesday after that, if I'm not mistaken. Yeah. So next Thursday's class meeting is on how power is actually measured. So how you would use a watt meter or multiple watt meters in order to determine all of the powers that we talked about in class today in a practical circuit. That realistically will take less than an hour to cover, and we can use the remainder of that class period as a review for the exam as well. So we've got plenty of opportunity in the next week, as well as tutoring session tonight and all of that kind of jazz for you guys to get a better grasp on this, okay? If you've got questions, I am more than happy to answer them. But I want you guys to start at least trying to sort this stuff out yourselves.